Me again. I am recording video 2 now of our limits units and video 2 of your AP Calculus journey. So the first video covered how do you deal with limits if something is presented to you as a graph. But here's something you're going to hear me say a lot, is that math is often described in 4 different ways. You have graphs of math, of functions, of relations, of things like that. So you have images. You have algebraic representations of functions, which is what you see here. You can also have numerical representations of functions and relations like tables and just lists of numbers and sets and things like that. And then you have verbal representations of math, which is me yapping at you, constantly. So we are going to explore and understand mathematics in those 4 different ways and make sure we understand the interconnectivity between them. So we started off with the graphical representation of limits and functions, and now we're going to move into the algebra, but I'm going to lean on what the graphs may have been doing from time to time. Okay? So day 2 of our limits unit is evaluating limits algebraically. So when we do this, there's a lot of ways to come about it, and we're not done even here on day 2 with algebraic representations of limits. We're going to do it months down the road as well. But the first thing we're going to talk about is what I call substitution, where you just kind of plug in the number and see what happens. So let's say for this first one, it says find the limit as x approaches 4 of x squared minus 10x plus 5. Technically, what we can do here is say, wait, that's an invisible 2-sided limit where I'm coming at 4 from the left and from the right. So I think about x squared minus 10x plus 5. I think about the graph of that function and say, do graphs of parabolas really have anything wrong with them? Are they broken? Do they have jumps or asymptotes or holes or anything funky going on? No, they're nice, smooth, U-shaped or upside down U-shaped things. So if I take the limit as x approaches 4, that's really going to be the same as the function value at 4 because nothing kinky's going on. So if I want to find this limit value, I'm just going to plug 4 in for all of these x values and see what happens. 16 minus 40 plus 5, well, let's see, 16 minus 40, that's negative 24. And negative 24 plus 5 is negative 19, I think. And that is going to be my answer. Okay? Do you need to know how to do that in your head? Yeah, you got to do some arithmetic in your head. If you want to check and have your calculator nearby, by all means, that's fine. But that is something you should be able to do without a calculator. Now, notice how I didn't just say that the limit as x approaches 4 is always equal to f of 4. It's not. But in this case, because I considered the fact that the limit as x approaches 4 means think about what happens from the left and from the right of 4, and I realize that's a parabola, I know that the limit and the function are going to be the same. Okay? Moving to the next one. The limit as x approaches 0 of the ln of e to the x plus 5 over the cosine of x. Wow. Okay? I've been teaching math for 24 years. I don't know what that function looks like. But you know what? I don't need to know what that function looks like. All I need to be able to do is think about what the function might be doing as x approaches 0. And say, all right, well, as x approaches 0 on the top, e to the 0 plus 5, that would just be e to the 5th, which is fine. And the ln of e to the 5th is also fine. I don't think anything weird's happening on that numerator. And if I think about x approaches 0 for cosine, the cosine of 0, well, that'd be 1. And the cosine graph isn't doing anything weird near 0. So what that tells me is even though this graph of ln of e to the x plus 5 over cosine x might be something crazy, and I'll show you what it is in a minute, it's not so crazy that I can't evaluate the limit near 0. So I'm going to plug 0 into the top and say the ln of 0, e to the 0 plus 5 over the cosine of 0 is going to be the ln of e to the 5th over the cosine of 0, which is 1. And the ln of e to the 5th is just 5. And so that's going to be 5 over 1, which is 5. And that's our answer. This limit equal negative 19 because of the work below it. This limit equals 5 because of the work below it. And the work we did in our head that said, let me consider, is something weird going on. And then over here, we've got the limit as x approaches 2. Okay, 2 squared plus 5 square rooted. Like, square roots can get weird near 0, or if I take the square root of a negative. But if I throw this 2 in there, it's not going to make that radical negative or 0, so I'm cool. And absolute value graphs can get weird and sharp and things like that, but absolute value graphs get weird and sharp when the absolute value is 0 or the inside goes toward a negative. And if I plug a 2 in there, it doesn't happen there either. So since I considered the potential pitfalls, and none of them seem to affect me, I'm good. So the square root of 2 squared plus 5 over the absolute value of 2 plus 7 is going to be the square root of 9 over the absolute value of 9, which is 3/9, which is a third. So that equals a third. And if you're curious, which I got to be honest, I am, what do these things actually look like? Let's see, if I go back into, I need to get to my regular Chrome tab, and if I go to one of my favorite websites of all time, which is Desmos, which you should absolutely bookmark, okay? Because the Desmos calculator is the one that is on your AP exam and on your SAT exam, and it's just a free and awesome calculator. Bookmark this. I know what a parabola looks like, but just for fun, if I put that parabola in here, it was x squared minus 10x plus 5, x squared minus 10x plus 5. Here is that graph, and if I shrink it down a little bit, and I say, what was that value at 4? Let's check. So I'm going to call this f of x, and then I want to know what's happening at 4, f of 4. There's my dot, and it's going toward negative 19. Ta-da! So there's that first one. And then let's see, the next graph we were looking at was ln of e to the x plus 5 over cosine x. Let's see. ln of e to the x plus 5. Got to put some parentheses around that to keep it up there. Let's see, ln of e to the x plus 5 over the cosine of x. Whoa, that's just cool, right? That's just cool. So that's where that thing is headed, and we wanted to know what was going on near 0. So I'm going to type 0f of 0 into there, and it says we're going toward 5. Is that what we got? Hey, that's what we got. Cool, cool. And then the square root of x squared plus 5 over x plus 7. Fun fact, if you're in Desmos and you're like me and you want a keyboard shortcut and you want a square root, you just type out squirt, S-Q-R-T, and it makes a square root. X squared plus 5. And if you want the absolute value, ABS. Oh, but it didn't work. Oh, you know what it is? I don't think ABS works. It used to. If you do shift, there's a vertical bar above the enter key. So I'm going to use that vertical bar, and that was x plus 7. Ta-da. All right, so that's what that thing looks like. Interesting. And for this one, we wanted to know what was happening at 2. And I got 0.3 repeating, also known as a third. So there's the connection between the graph and the function. Okay, and the graph and the algebra. All right. So going back to algebra, though, I am not going to flip-flop back and forth all the time, but I will a little bit. And you can always use graphs to back up what you see in the algebra. So let's come down here and say, what's going on if I did a one-sided substitution? Well, if I do a one-sided substitution, I need to think about it just like we did in the last case. Rewrite the expression in piecewise form, because if I want to come from one side or the other side, I'm thinking of the graph in pieces. And then basically find your answer. So for this first one, if I wanted x coming at 2 from the right, I would need to say, okay, if I'm coming at x and it's 2 and it's from the right, those are values greater than 2. That means I'm looking at whatever piece of the domain includes numbers bigger than 2. And so if I think about numbers coming from bigger than 2, I'm really going to throw 2 into this expression piece of the function. So 2 plus 1 is 3. And so the limit as x approaches 2 from the right is 3. Okay. All right, what about 3 from the right of x minus 3 over 3 minus x? So here's the thing. Calculus and absolute value, they hate each other. Okay, they are not friends. Absolute value just is kind of garbage for our case. So what we do is we say if I have absolute value, I got to write it in piecewise form, whether I'm taking limits or later down the road doing derivatives or later after that doing integral. Anytime we see an absolute value, we go, ugh, I got to write a piecewise form of this. So I'm going to. So let's see. I'm going to rewrite this and say x minus 3 over 3 minus x in absolute value is the same as x minus 3 over 3 minus x for when the inside is already positive, but it's going to be x minus 3 over negative 3 minus x for when the inside would have been negative, and therefore we'd negate it to make it positive. So I say, okay, what x values are going to keep this bottom stuff positive? Well, 1 would work, 2 would work, 3 it's going to be 0, and 4 is when it starts kind of going into the negative. So 3 is your flip over point. So when x is 1 and when x is 2, it's already positive. So when x is less than 3, the absolute value doesn't make a difference. But when x is bigger than 3, the absolute value does make a difference, because when x is bigger than 3, like 4, 3 minus 4 is negative 1, the absolute value takes the negative and makes it a positive. Then I'm going to say, wait, this is really confusing. Can I simplify this? Yeah, you can. You can say, wait. X minus 3 over 3 minus x is negative 1. And x minus 3 over 3 minus x is negative 1. So x minus 3 over the absolute value of 3 minus x actually is negative 1 when x is less than 3, and negative 1 divided by another negative 1 is positive 1 when x is greater than 3. And you might be thinking about, wait, what about right at 3? Well, here's the problem. This function doesn't exist at 3. Because if x equals 3, the denominator equals 0, so the original function's undefined at 3. So I don't need to have anybody underlined. Okay, what were we doing? Oh, right, we were supposed to find a limit. So I needed to find a limit as x approaches 3 from the right. So let's see, as x approaches 3 from the right, that's when x is bigger than 3. That means I'm looking at this, and apparently when x is bigger than 3, the function just equals 1. Cool. Okay. All right. Last one. All right. As x approaches negative 8 from the right. All right. As x approaches negative 8 from the right. Oh, man. But I got that absolute value again, so I got to rewrite this one more time. And let's see. That's going to be the square root of 2x plus 16 plus 5. Over x over absolute value of x really becomes the square root of 2x plus 16 plus 5 divided by x over x when x is already positive and the absolute value doesn't make a difference. So when x is greater than 0, that's how that works. And the square root of 2x plus 16 plus 5 over x divided by negative x For when the absolute value interior is negative and we negate it, we're going to negate x when x is negative. In a nutshell for that, you basically want to split your absolute value into two parts. The first part being when the absolute value's interior is greater than 0. The other part when the absolute value's interior is less than 0, and it's going to switch over when the absolute value interior equals 0. Over here, the interior of that absolute value equals 0 at 3, so we split it at 3. Over here, the interior of the absolute value equals 0 at 0. Okay? All right. But again, what were we supposed to do here? We're supposed to find the limit as x approaches -8 from the right. So that's like slightly bigger than -8, so like -7.9. That would put me into here. Okay, so let's see. If I plugged -8 into this piece, that's going to be the square root of 2 times -8 plus 16 plus 5 over -8 divided by -8. That's really just going to go to -1. This is -16 plus 16. That's going to be 0. So what I really have is 0 plus 5 divided by -1. That's -5. Whew, that's a lot. This is going to be a longish video because I'm trying to explain a bunch of things all at once. Now we got more on the back. On the back, we have 3 more to do. I'm going to try to yap a little bit less, but basically tell you that calculus exists because not all functions are nice, smooth, W-shaped, U-shaped things. They get broken with asymptotes, with cusps, with corners, with all kinds of things. And calculus is there to say, listen, even though this is ugly, I can still help you describe it. Okay, so when we come to the back, we're going to have a bunch of limits of functions that are broken, okay? And so when we see that happen, we're still going to start by substituting in, but realize that that substitution is going to be broken, and then we're going to fix it. So let me explain. On number 1, it says, find the limit as x approaches 4 of this rational expression, 16 minus x squared over x squared minus 2x minus 8. If I were to just plug 4 into here, I have 16 minus 4 squared, which is 16, over 16 minus 8, and that goes to 0 over 0, which means my function is broken. And when a function is broken, lots of things can happen, but specifically, when a function is broken and that function goes to 0 over 0, that means that it might be fixable. It means that you might have a limit that exists even though the function has a hole in it. And to see what's going to go on, is it broken in a fixable way or is it broken in an unfixable way, what we try to do is simplify the expression. We say, all right, if I take 16 minus x squared, that's going to be 4 minus x times 4 plus x. And if I take x squared minus 2x minus 8, that's going to be x minus 4 times x plus 2. Okay? So x minus 4 and 4 minus x do cancel and divide to -1, which means this original expression can be simplified into this other expression, and their limits are the same. So that original limit can also be written as -4 plus x over x plus 2. And now, if I plug 4 in, I get -4 plus 4 over 4 plus 2, which is -8/6, which is -4/3. Okay? And there's our final answer. Now, here's the part where I'm going to kind of ramble, and even though you're not writing anything down, I need you to listen to me. I wrote this in a very specific way, and I put my work in a very specific spot because everything I wrote down was correct. But if left to your own devices, you're going to write down things that are mathematically incorrect, which may seem like no big deal to you, but they kind of are a big deal because calculus is the world where everything that's broken goes. We need to be very careful about the way that we deal with things. What do I mean? Well, here's what I mean. I am going to write some stuff down here in red. I do not want you to write it down. One of the things I'll see a lot of people do is they'll say 16 minus x squared over x squared minus 2x minus 8 is equal to 4 minus x times 4 plus x over x minus 4 times x plus 2, and that's correct. But then people come in here, cancel that, put a -1, and say that that is then equal to negative 4 plus x over x plus 2, and that's not correct. Those three things are not equal to each other because this expression is undefined when x equals 4, but its canceled equivalent is defined at x equals 4. And that's a problem because in the world of mathematics, this symbol equals means equals for any x value you can pick. So what I will often do to avoid that misuse of an equal sign is I don't put an equal sign when I'm just thinking. So like right here, I just said, well, if I were to plug in 4, here's what would happen, and it goes to 0 over 0. But that's not the answer to the limit. I never said the limit equals 0 over 0. I said that when you plug 4 into that expression, you get 0 over 0, which made my brain think, wait, if the top equals the bottom, there are things that might cancel. So then I came down here, and I said, all right, let's do some of that canceling. Notice, none of that stuff in blue is set equal to anything else because I knew that what I was about to do is going to create a new expression. Here's where I did use an equal sign. Even though those expressions, this thing and this thing, even though those expressions are not equal, the limits as x approach 4 for those expressions are equal to each other. Okay, and that's what we have going on here. Now the problem is my phone is ringing. Can I pause this? I can't, so they're going to have to wait. All right, so when I did that, the limits are equal even though the expressions are not, and that's why I linked everything as I have it there. Okay, moving on. I know this video is getting kind of out of control. It will not always happen, but if I have a video that goes more than 20 minutes, I need you to stick with me. All right, number 2, we're going to do in much the same way. We're going to say, all right, as x approaches 9, what's going on? So I throw the 9 into there, and I say, okay, the square root of 9 minus 3 over 9 minus 9 does go to 0 over 0. That's undefined. The limit might still be defined, but right at 9, that expression is undefined. But since it's a 0 over 0, it might be undefined in a way where it cancels out. So I'm going to say, well, how can I deal with this? Well, I have the square root of x minus 3 over x minus 9. One of the things you might have learned in Algebra 2 or in pre-calc is that you can rationalize expressions. And so I'm going to rationalize this and say, you know what, my numerator has a radical on it. And simply because I can, I'm going to multiply the numerator and the denominator by the conjugate of that numerator. So if I multiply by the conjugate of the numerator, I am going to multiply that numerator out, and that's going to become x plus 3 root x minus 3 root x minus 9. And I'm going to leave the denominator alone because the denominator was not the thing I was trying to simplify. So I'm not going to distribute on there. And then I'm going to say, well, these things cancel out, and that leaves me with x minus 9 on top. And so x minus 9 on top cancels with the x minus 9 on the bottom, leaving me with a 1. Notice I haven't used an equal sign because I'm just trying to be careful here. And say I'm just simplifying. And it seems that I can simplify this original expression into 1 over the square root of x plus 3. And then if I plug 9 into that expression, I get 1/6. One more. Whoa. Flat fractions within fractions. I got complex fractions. Gross. All right, well, let's see. What happens if I plug in 1? If I plug 1 into here, I have 1 minus 1 over 1 minus 1. That goes to 0 over 0. That's undefined, but it's undefined in a way that makes things maybe cancel out. So I have 1 minus 1 over x and 1 over x squared minus 1. I'm going to make everybody a fraction. And then to make everything easier, I'm going to multiply by what would be a common denominator for all 4 fractions involved. I'm going to multiply this entire numerator by x squared. I'm going to multiply this entire denominator by x squared because I can. Because I'm multiplying by x squared over x squared, I'm multiplying by 1, which changes the look of, but not the value of, what's going on there. And so if I do that, I'm going to have x squared minus 1 over x times x squared is just x. And then distribute that x squared, I'm going to have 1 minus x squared on the bottom. That can factor to x times x minus 1, and 1 minus x times 1 plus x. These divide to -1. Notice I haven't used an equal sign because I know I'm artificially eliminating some things that would be undefined. So my original limit can now be rewritten as -x over 1 plus x. And as x approaches 1, that's going to be -1 over 1 plus 1, which is -1/2. Okay? All right. Last thing. If these last 3 expressions were all graphed as functions, what would the graphs look like at the point of the discontinuity? That's where the 0 over 0 in our case was, where the thing was undefined in the first place. And the answer is they would be wholes that are connected on both sides. Okay? So if I graphed these, what I would end up with is I would say as x approaches 4 up here, the y value would go to -4/3, but it would have an open circle there. All right, and I'm going to do just one of those on Desmos. Let's see, this first one was 16 minus x squared over x squared minus 2x minus 8. Never wants to delete the way I want it to. 16 minus x squared over x squared minus 2x minus 8. And we were trying to deal with that as x approaches 4. And it says, wait a minute, f of 4 is undefined, but we got a limit that equals -4/3. So let me show you what that looks like. So I'm going to do a comma f of a and make a slider, and I'm going to start at 3 and go towards 5 and make my slider here. Oops. There we go. And if I look at my slider, see it kind of on the graph there? If I look at my slider, as I go toward 4, I'm getting negative 1.37, negative 1.36, and then right when I get to 4, it's undefined. Negative 1.3, negative 1.3. So there's definitely something going on in the neighborhood of a y value of negative 1.33. Well, guess what? Negative 4/3 is negative 1.3 repeated. All right. I'm sick of listening to myself talk right now, and I'm sure you are too. So hopefully a lot of this made sense. There's some nuance here, and I need you to pay attention to that just as much as you pay attention to these answers. Okay? So hopefully this made sense. This was long-winded. I promise not all videos are going to be this long, but your second one was. Have a wonderful rest of your day, and we'll talk soon.